I'm going to give the lecture for Chapter 9, Alkynes, in two parts. In the first part, I'm going to talk about the general concepts of alkynes, properties, nomenclature, and how they can be made from other functional groups and some of their reactions. And then we'll get into another section of this chapter when we talk about some other things that we can do with alkynes. When we say the word alkyne, what we mean are compounds that contain at least one carbon-carbon triple bond. And remember that there are 2 points of unsaturation for every triple bond. Both of the carbons are sp hybridized, which means that there are going to be 4 atoms in a line because the bond angles around sp hybridized atoms are 180 degrees. It's linear, and the 2 pi bonds that are in the triple bond are at right angles to each other. So anywhere you have these features in the molecule, you'll have those 4 atoms in a line, and since they're linear, then you don't have to worry about cis or trans geometry or E or Z or any of that stuff. And there are some naturally occurring alkynes found in nature, and of course we're also interested in how we can make them. Now you have a total of 3 bonds between these 2 carbons. So overall, the total is stronger and shorter than a carbon-carbon double bond, but the total strength is not twice as strong as you would think you would get if you had 2 pi bonds each by themselves. And you could kind of do a back-of-the-envelope calculation for that. But what it means is that the alkynes are a bit more reactive than the alkenes, although there's some kind of differences and some similarities. So for nomenclature, we're going to take the alkane word for the parent number of carbons and replace the internal A with a Y. And there are also some common names. And of course, the sort of the parent molecule is the 2-carbon molecule, and the common name for that is acetylene. And the 2-carbon alkane would be ethane, so the IUPAC name is ethyne. If you have a chain of carbons kind of the same way as with alkenes, you have to number through the triple bond. So you find the longest chain, start numbering at the end closest to the triple bond, and go through the double bond. And so, for example, you might get a name like this because we started at this end closer to the triple bond. We have a total of 8, so 6-methyl-3-octyne, or in the new style you can put the 3 inside the word right before the -ine, which is what it's modifying. If you have both carbon-carbon double bonds and triple bonds, then you kind of want to take that rule of numbering at the end closest to the double bond or triple bond and look at all the possibilities and try to minimize all of the numbers. So there's no rule about whether the triple bond or the double bond takes priority. They're considered pretty much equal in the numbering system. It's just where do you get the first thing. So suppose you have this one. Well, then there's a tie. You're going to get a double bond at carbon number 1 and a triple bond at number 6, regardless of if you get 1 here and 6 there. And so then your fallback position is alphabetical. Since "ene" comes before "eine," we're going to write that down first, and so then we'll give that one the smaller number. But that's only in case of a tie. And here's the 2 styles of writing that down, either the one out front or inside the word, and the 6 has to be inside in that case. So here's a case where there's not a tie. So we can get a multiple bond at carbon number 1 and the other multiple bond at number 7, and that's smaller numbers than if we'd have started at this end. We wouldn't get to 1 until number 2, and so on. So that's the best way to number that molecule. And again, here's the 2 styles of writing that down. The 7 either in front of this part of the word or open it up and put it inside of there. We do write "enes" first and then "ines" because of the alphabetical order case. And so here's one more example. This one is a diene and alkyne. And so if we start numbering from either end, we get to a multiple bond at 2, 4, and 6, either way. since the enes come before the ein, alphabetically, even if you're using the prefix di, we're going to start numbering from that side. So a good name for this is 2,4-octadiene. So we put the numbers out here in front, and they modify this part of the word, and then the 6 for where the triple bond is. Or if you would have numbered it this way, you see why these numbers, the red numbers, turn out to be smaller than if you would have used the blue numbers. So that's what we're talking about, trying to give the smallest numbers as we can. So the preparation of alkynes excuse me, can be done kind of similarly in some ways to the alkenes. If you want to make a triple bond where you have no multiple bond, then you could do the same thing as making alkenes. So you could take out the elements of HX and do dehydrohalogenation. But since you want to make two bonds at the same time, you need 2 molecules of HX. And sometimes you can also start from a molecule that's already got a double bond in it. So this example that I've got here is starting from an alkene, you could make a dihalide. And so in case you were wondering how you can find a molecule that has 2 elements of HX to take out, well, you could have started with an alkene, you put your 2 bromines in there, now we can take out an HBr across here and an HBr across here, and we can get to here with 2 molecules of base. By the way, this kind of molecule is called a vicinal dibromide because they're on adjacent carbons. And it says up here in the notes that aromatic rings are inert to these conditions. In other words, aromatic rings are not alkenes. They really are different. Even though they kind of look like alkenes, they're really not. They don't act like that at all. So you can do this kind of reaction on the alkene and not bother the aromatic rings. And because there's no hydrogen here or here, then when we get to this stage, there's no choice. If we're going to take out 2 molecules of HBr, this is the only place they can come out, is to make this. So this guy is set up so that it can't fail. If it's actually going to create 2 pi bonds, there's only one place that they can go. Another thing you could do is you could have a problem occasionally that when we're trying to take out these 2 molecules of HX, maybe the 2 KOHs isn't strong enough. Remember that the pKa of hydroxide ion is about 16, and so sometimes you need a stronger base. And the stronger base that is popular for this particular application is to use the anion from ammonia. Now, I know you remember that ammonium hydroxide is a weak base, but we're not talking about an aqueous solution. We're talking about ammonia all by itself can act as an acid and give you this NH2 minus anion. The pK of ammonia, not in water, just plain ammonia, pK is about 35. So that's a lot stronger than water, whose pK is about 16. So if you have some of this, then you can use that base. And so it comes as a salt just like hydroxide does. Or you can make it if you need to. And so we can take out the elements of HX here. Now this particular example that I got out of the book already has 1 double bond, so we're taking out an extra HCl, and this kind of process is, maybe this is a little harder to do, so they wanted to use the sodium amide. This is what this is called, is sodium amide. Now one question you might ask is, well, why do we need 2 molecules here when we're only taking out 1 molecule of HCl? And the answer is I wouldn't have picked this example, but the answer that this is actually acidic. This is similar in pKa to water. And so one of these molecules is going to react with this and make a salt. And then the second one is going to take out the HCl, and the purpose of the aqueous acid here is to reprotonate this and to get rid of the leftover stuff from that. And like I said, I wouldn't have picked this particular example because of this extra complication. But the main thing you need to know is that if you have this is called a vinyl halide, you can also make alkynes out of that. Alright, so now you know a couple of things that you can do to make alkynes. So let's see what we can do with those. And in order to do this properly, we need to review a little bit about alkenes. So we talked about the reaction of alkenes. We talked a fair amount about the electrophilic addition reactions of some things with alkenes. And so here's how that started. The alkene pi bond acts as a Lewis base. The positive end of an HBr is the Lewis acid, and then that breaks this bond, and you get that carbocation. And remember, we had the more substituted carbocation would form, and the hydrogen would go to the less substituted carbon. We talked about that a lot. And then in the second step of that reaction, the bromine ion makes the bond, and so you got an alkyl bromide. And there was a lot of discussion about that. Okay, so if you were going to do exactly the same thing with an alkyne, and again, this kind of drawing from the book doesn't show you the different degrees of the carbons, so we won't worry about that right this minute. But if you started out using one of these pi bonds to get the positive end of the HBr and kick this out, then the carbocation that you get looks a little different than the carbocation we got from the alkane. This one was an sp2, and it's still sp2. This one is sp, it's still sp. And the whole thing about why we made the more stable, the more substituted carbocation was the concept called hyperconjugation. So nearby CH bonds can help fill this empty orbital and leak a little electron density over, and that's why more and more of those you put around this guy, the more stable it would get. Well, if you look at this guy, it's a slightly different angle, and also there's not as many carbons around it, and so even if you have another carbon over here, it has, even though it's secondary, it actually has not quite as good of an ability for this bond at this angle to overlap. And so here's some pictures that kind of help show you that how these things look. So the hyperconjugation orbital is not quite as easily stabilized as the one on the alkene that turns into an alkyl carbocation. So the products are different. Also, we have an alkyl bromide versus a vinyl bromide. And so hopefully these pictures can help a little bit. Alright, so now I'm going to do another example in still a generic situation where I've got now an R group on here and a hydrogen here, so I have two different degrees of carbon. This alkyne is going to be a terminal alkyne because it's at the end of the chain. And that's the only time when an alkyne will have two different degrees of carbon. If it's internal to a chain, then both carbons will be secondary. Remember, all we're counting is how many carbons the carbon is attached to. So if we start out doing this HX reaction, then the pi cloud of electrons is going to react with this and put the hydrogen on the less substituted carbon, and then the halogen can bond and make this guy. So there's your vinyl halide is the first product, and then that can react again. And so I've now got the partially positive and negative charges on here. Again, putting the hydrogen on the less substituted carbon, and the carbocation that forms from that will then get the next halogen. And in case you're wondering, will that carbocation still be more stable on this carbon as opposed to the N carbon? The halogen can actually help stabilize this. So this is the resonance stabilization of that internal carbocation. So it's still going to put the hydrogen on the less substituted carbon and the other halogen on the same carbon with the first halogen because of that resonance stabilization. And X can still be any one of our three common halogens. And like I said, the only time you can really see a difference in the products is if you're talking about a terminal alkyne. Otherwise, you're going to get mixtures. So here's an example. And one question you might ask is, how hard is it to stop at the vinyl halide? In other words, if we put in a 1-to-1 ratio here, can we stop here, or do we just keep going? You know, and the answer is, it's really hard to stop, because we talked about the fact that this reaction is pretty easy to a certain extent, because the triple bond, those pi bonds, are not really quite as strong as the single pi bond. And it's really hard to make it stop. And so a lot of times people just plan for it. So they just go ahead and say, well, I'm going to put in 2 molecules of HBr, and we'll just go ahead and go over here. Here's some more examples where, you know, the book shows that you could stop. And if you have some way to measure the reaction product as it forms, you maybe could enhance how much of this you get. But it is kind of tricky to stop here in the middle. And so if you just go ahead and go directly from here to here by putting in 2 molecules of HCl for each alkyne. Now you notice that this molecule is internal, so both of them are secondary, but it's also symmetrical. We have the same stuff on both sides. So when you get to here, you can't tell the difference as to which carbon got the hydrogen, which carbon got the chlorine out of these original 6. One or the other, you know, got the hydrogen, and the other one gets the chlorine. But remember that when you go again, that the carbon that has the halogen on it will be resonance stabilized if we put the carbocation there. So we know the second chlorine is going to go on the same carbon as the first chlorine. So another thing that you can do is you can add halogen molecules like we did with alkenes. And again, it's kind of hard to stop. And so if you just plan for it to just keep going, then you'll just get a bunch of halogens, you know, 2 on each carbon. And again, it won't matter what the degrees of the carbons are. In this case, you're going to just get a single product by the time you add both of them on there. If you were trying to stop here, you can tell that they are still coming on opposite sides like they did with alkenes. And if you're trying to stop there, then you've got to have some way of monitoring the progress of the reaction in order to catch this guy before it reacts again. And remember, those 2 bromines are on opposite sides because they do anti-addition here, just like they did on the alkenes. Now, we're not going to do every single reaction that we did on alkenes on alkynes, but we are going to talk about the hydration of alkynes. And remember, with alkenes, we went through an intermediate carbocation, but we added the molecule of water across that double bond. And now if we add 1 molecule of water, we're going to get to a molecule that looks kind of like this. So you've put a hydrogen on here and an OH on here, and at this stage of the game it looks like Markovnikov addition. And you'll notice that we have some different conditions, kind of like a combination of the industrial route, which was sulfuric acid followed by water, and the oxymercuration route, which used the mercuric acetate. Well, for this we're going to need a mercury plus 2 salt, and usually they use the anion is the same anion as the acid that they're going to use. So you need an acid, you need water, and you need a mercury plus 2 salt, and it's a catalyst. And so once you get that, and we have 2 different degrees of carbon, then we're going to put Markovnikov addition, put the hydrogen and the OH on it, and we've got this molecule drawn in brackets. Now what that means is that we can't stop there. Even if we wanted to, you can't keep it. And this guy is called an enol for the ene and the alcohol, or we also call them vinyl alcohols. Remember, anything that's directly attached to the alkene is called vinyl whatever. So there's a vinyl alcohol. And this is actually an equilibrium. They didn't draw the equilibrium arrow, but the equilibrium lies really far to the right with a carbonyl. So it's kind of like you take this pair of electrons and get this hydrogen, and then that bonded pair of electrons comes back in here. And so you just move this hydrogen over to here, and the electrons flip around, and so you get a ketone out of that. So a terminal alkyne can make methyl, this is a methyl group, a methyl ketone. And so just a little bit more information about that. The triple bond complexes with the mercury, then the water will react with the carbocation that forms on the more substituted carbon, and then it'll lose a proton. And so here's your vinyl alcohol, except that it's got this mercury on it, which is going to come off in the presence of the aqueous acid, which we've also got in there. So here's your final vinyl alcohol, which we can't stop at, and it goes ahead and rearranges to this other form, the methyl ketone. Now that equilibrium thing that I've been talking about, here's one form, the vinyl alcohol, and here's the other form, the keto form, or the ketone. And this form is more favored. Now, if you're sitting with a flask or a test tube with some ketone in it, there'll be a little bit of this in there. That's what this means. It doesn't have to be in the solution. It's sitting here doing this, but mostly it's over on this side. So maybe, 85% of it looks like this and 15% of it looks like this, but it's still going to behave like this. So you can't stop this from happening. So the bottom line is that when you do the hydration on an alkyne, even though it has two quote-unquote double bonds or two pi bonds, you're still only going to observe that it takes up 1 molecule's worth of water. So here's another example. So here's my terminal alkyne, and we make as a product a methyl ketone by way of the Markovnikov vinyl alcohol. And so that one had 2 different degrees of carbon because this one is primary and this one is secondary. If you have an internal alkyne, and here we've got R and R prime to indicate that this might be 2 different chunks of carbon, and you do the same thing. Now they're both secondary. I can't really tell the difference between them. The reagents can't tell the difference between them. There's no steering currents. So you're going to get some of each of the possible vinyl alcohols, which is going to lead to the 2 possible ketones, and you'll make a mixture. That means that if you don't want to make a mixture, then you should try to avoid having an unsymmetrical internal alkyne. What if it was a symmetrical but internal alkyne? Then what would happen? If these 2 guys are the same, like 2 ethyls in an early example we had, then it wouldn't matter. You'd still only get 1 product. So here's an example to practice on. Now this guy is an unsymmetrical internal alkyne. So that means that we could put some of the OH here with the hydrogen there, or we could put the OH here with the hydrogen there. It's not going to matter. So let's take a look at the enols. Okay? So if we put the OH on this carbon and the hydrogen there, we get this enol. If we put the OH here and the hydrogen there, we get this enol. Okay? And when those go to the carbonyl form, we're just going to move this hydrogen over here, and this is going to become a carbonyl. We move this hydrogen over here, and this is going to become a carbonyl. So we draw pictures of those, and here's our equilibrium that it mostly exists in this form. We see those are not the same 2 molecules. So we're going to make the mixture from this alkyne with hydration conditions. We're going to make a mixture of these 2 products. So then we could look at this question. If we had this set of conditions and we have a ketone product, we now know that one way we can make that is with the hydration of an alkyne. So the next obvious question is, okay, where in this molecule was the triple bond? And we know it has to have been on this carbon and one or the other of the carbons on either side of it. Now here's the question. Which one would be the better choice? If you put the triple bond between these 2 carbons, then you'll have 3 on one side and 3 on the other, and that would have been a symmetrical internal alkyne, and this would be the only product. You could have put the triple bond between these 2 carbons, but then it would be an unsymmetrical internal alkyne with a 2 and a 4 carbon chain, and then what? Then you get a mixture of this product and another product. So here's the enol, and again, if you draw it like this, you can see it doesn't matter which carbon we put it on. If this was where the original triple bond was, we'd have 3 carbon chains on either side, and so this would have been the best starting material to make that. Now, another hydration that we looked at in the alkenes chapter was called hydroboration, and that one followed a completely different mechanism, which we didn't go into very much detail on, but we knew that it gave us the anti-Markovnikov product. And the anti-Markovnikov product was one that meant that the hydrogen went to the more substituted carbon, and the OH went to the less substituted carbon, which is the opposite of what Markovnikov said. And the same thing is going to happen here. We can react the alkyne with borane, and if it's a terminal alkyne, and we have 2 different degrees of carbon, then we can see a preference for the boron to go to the less crowded carbon and ultimately get replaced with an OH. We're again going to balance the equation with 3 of these and 3 of those, so we get 3 product molecules. This vinyl alcohol is in equilibrium with this. The equilibrium lies very strongly toward the carbonyl form, which in this case is an aldehyde. The only time you're going to get an aldehyde is if you had a terminal alkyne. You have to have an aldehyde at the end of a chain, and there's your hydrogen. That's the only way you can get an aldehyde. If you have an internal alkyne, you can still do this kind of hydration, but you're going to get exactly the same results as if you had used the mercury route. And I told you that boron will react with 3 molecules of the alkynes or alkenes, and it gets steered because of crowding. So all 3 of these alkynes have reacted one at a time, and all 3 of them are surrounding that boron. So you see why, if there was a difference in degree, why it would want to go to the less substituted carbon. Now here it doesn't matter, so we're just going to see this intermediate, if you will, and then we do the hydrogen peroxide in aqueous basic solution, and we get rid of the boron and replace it with an OH, and because this is symmetrical, it doesn't matter which carbon got which. So the enol is drawn in brackets, and we turn that into a ketone, an internal ketone, and either carbon, you get the same result. If you had a terminal alkyne and you do this, now they haven't drawn all of this stuff out here, they just abbreviated it all with R's. But if you put all that out there, then then you can get the terminal alkyne will lead to an aldehyde, and you can only get aldehydes if you had a terminal alkyne. All right, so let's just sort of put those things together. If we have a terminal alkyne and we use the mercury catalyzed acidic aqueous solution, we can get a methyl ketone if we started with a terminal alkyne. We get Markovnikov orientation, the hydrogen goes to the less substituted carbon, the OH goes to the more substituted carbon, but ultimately becomes a carbonyl. If we have a terminal alkyne and we do hydroboration, the boron goes to the less substituted carbon. Ultimately, it gets replaced with the oxygen, and the hydrogen goes to the other carbon, and that's how you can get to an aldehyde. Another thing that we did with alkenes was we talked about reduction. So in other words, adding hydrogen across the pi bond of an alkene, and that works also on alkynes. And we could use platinum, palladium, or sometimes a nickel catalyst, the same as we could for alkenes. Remember, the deal was that the catalyst surface captures the hydrogen molecules, and so they're adsorbed onto the surface of the catalyst, so they're delivered to the same side of the double bond. And that enabled us to conserve the geometry. If we had a cis alkene, we could make a cis molecule where we could tell, like on a ring, with the hydrogens coming from the same side. Now they give you some information here about heats of hydrogenation, and going from the triple bond to the double bond is more exothermic, so it's easier to do that step than, it's more favorable to do that step than it is to go from an alkene to an alkane. You have a difference in how much energy you get out from doing those two reductions. So people looked at that and they wondered if there would be a way to stop. Now if you use these catalysts, those are the same ones that work on alkenes. So if you're using any one of these same old catalysts, you can't stop. It's just going to go right on down. We can't say we're just going to put in a 1-to-1 ratio of hydrogen. Remember, the hydrogen is bubbling in and we don't capture all of it anyway, and so we can't really plan on just putting in a 1-to-1 ratio. It's just not going to work, and this reaction is going to be going on too. So people needed to find a different way, a different catalyst, or somehow modify the catalyst in order to be able to stop it from going on. So there was a guy that did a lot of work on this, and his name was Lindlar, and he found a way to modify a palladium catalyst, and it's considered a poison on the catalyst because it modifies its activity. And so you take this combination of palladium, instead of suspending it onto carbon, they use calcium carbonate and quinoline, and here's a picture of quinoline. And ethyl acetate is a solvent instead of ethanol. Now you don't need to memorize all of that stuff, but you should know that Lindlar's catalyst is the thing that will stop at an alkene from an alkyne. And since both of the hydrogens are going to be delivered from the surface of the catalyst, we're only going to make cis alkenes. Now you have another option for partially reducing alkynes and stopping at alkenes. You know, if people figured out a way to make only the cis alkenes, it stands to reason somebody would want to also be able to make only the trans alkenes. And so the way that you do that is with an alkali metal. You can either use lithium or sodium. Most of the examples in the book are using lithium. And you dissolve that in liquid ammonia. And liquid ammonia is at minus 120 something degrees, so it's really cold. And when you dissolve this alkali metal in it, it makes a really bright, brilliant blue color. We call that color electric blue, and it's like dissolved electrons. Because remember that these alkali metals are really easily able to give up their outer shell electrons. And so what will happen is that when you put this alkali metal into the liquid ammonia and it turns blue, then you put in your alkyne. Well, it's going to deliver electrons to the alkyne, but they're going to try to stay away from each other. And so as you get enough electrons in there, then you've got a pair. You can pick up a hydrogen from the ammonia, and because it's always trying to keep those odd electrons away from each other, it favors making trans molecules. So you get trans alkenes out in pretty good yields. So to sort of see some examples, here's a symmetrical internal alkyne. Hydrogen gas over Lindlar's catalyst, we're going to make a symmetrical cis alkene only. And if we used a regular catalyst that we normally would use for an alkene, we'll just go to octane. Now, could you go directly from here to octane? Yes. You just put in hydrogen with the palladium catalyst, and you can go directly from the alkyne to the octane. And so if you instead put in lithium and liquid ammonia, then we can specifically make the transoctene. And again, if we put in hydrogen on that, we'll get to octane. So either route, you could either stop or you could just go on. But these two sets of conditions, the Lindlar's catalyst or the liquid ammonia, the dissolving metal, will stop at an alkene. So it's important to keep that straight. So what happens if you have a terminal alkyne? Will it still work? with either of these conditions? Well, yeah, it's still an alkyne. So here's an example. We could make this molecule by one of two routes. Here it is again. And we can also make the alkane. So what do you use? Well, if you want to make the alkane, you just put in hydrogen over one of your typical catalysts. If you want to stop at an alkene, then you can either use the lithium and ammonia, or you can use Lindlar's catalyst. I can't tell the difference between these two molecules. Can you? It doesn't matter. Either one of these will still work just because it's a terminal alkyne. It doesn't matter. It's going to stop at the alkene. Now, something else that we looked at with alkenes was the oxidation of alkenes. And one of the things that people do when they oxidize alkenes, sort of the logic for why that was interesting, is that they would use those reactions to figure out what was the original alkene, because they look at the pieces that you get out. Now, in the case of alkynes, because you have 3 bonds between the same 2 carbons, it doesn't matter which set of conditions you use. With permanganate or ozonolysis, followed by zinc, in aqueous solution, you're going to get carboxylic acids. Every one of these carbons is going to become a carbonyl with an OH on it. It's not going to matter what else is on there. You're going to make carboxylic acids. Unless you have a terminal alkyne, in which case, because you have this hydrogen here, remember how that would keep getting oxidized? And it's also going to go all the way to CO2 here, even with ozonolysis, because you had this triple bond. So that's the end of the first part of this chapter. And so when we go on in the next part of the chapter, we're going to look at some other things about terminal alkynes that are kind of interesting, that we'll be able to use those to make bigger alkynes, which is a little different than what we talked about earlier in this section. We talked about if you did not have a triple bond, how could you create one with double dehydrohalogenation, for example. So this is going to be different. We already have the triple bond. We're going to utilize it to make a bigger molecule. And that whole idea of making smaller pieces into bigger pieces is something that's going to follow us through all the rest of our studies of organic chemistry. So I'm going to stop this section now.